So what I'm going to do is I'm going to take the data that we had from the Hess's Law Lab that you guys did a couple weeks ago, show you how to do the calculations. It's real simple, won't take you very long. The whole point of Hess's Law is to prove that you can take delta H from different reactions, add them together, and they equal an overall reaction. So that's Hess's Law. So how are we going to do that? Well, basically what we're going to do is we're going to first calculate Q. I'll show you how we're going to do that. Then we can convert to kilojoules, which is really just dividing by 1,000. That's all you're going to do there. Then finally, you're going to divide by the number of moles, and you end up with delta H, which is the same thing as heat of a reaction that we'll add. So, first thing you're going to start, or the first place you're going to start is going to be your graph. Your graph probably looked like this the day we did the lab, and you had to extrapolate it back to where it crossed the Y. That point where it crosses the Y is T final. That is your temperature final. Your temperature initial comes from measuring the two before you start and average them together. So somewhere in your notebook, you should have wrote down what the average temperature was, average them together, and that's your temperature initial. So T final, that's why you need to have your graph. You need to mark it on your graph. You highlight it, it tells you what the y-intercept is. Like this one is 41.5 would be my T final. I'm just using this as an example. Yours probably was not that high, but basically that's why we use the graph. First thing we have to do is we have to calculate Q. How are we going to calculate Q? We're basically going to use this equation right here. This is the normal thermochemistry equation we're used to, which is Q is equal to M C delta T. We also add on a little bit for the calorimeter, because the calorimeter, the coffee cup, absorbs heat. It actually absorbs 11 joules for every degree that your delta T, your temperature, your solution changed. So when you go to do the setup, it's very similar. You're just adding this little piece on to take care of what the coffee cup does to find heat of reaction. Well, we used 50 milliliters of solution, 50 milliliters and 50 milliliters. Our assumption, we're going to assume that that's going to be equal to 100 milliliters, which is the same thing as 100 grams. So every one of your calculations, the mass is going to be 100 grams. The specific heat, we're going to assume it's water, is 4.184 joules per gram degree Celsius. Where it is right there. Delta T, that's going to be based on your data. I'm going to make one up. I'm going to say 41.5. I'm going to say my initial temperature was 20. So to find my delta T, my final is 41.5 minus 20. I'm just making these numbers up. I'm going to get 21.5 right there, plus 11 joules times 21.5 right there. That'll account for the coffee cup. When I calculate this, I'm calculating the heat absorbed by the water in the coffee cup. That, if I change the sign to the exact opposite, it is the heat basically lost by the reaction. That's the whole point. So I'm going to do this calculation really quick. So basically what I'm going to get when I do my calculations is this times this times this is going to give me, and remember I made these numbers up, so they're not going to be like similar to what you had in your lab. I'm going to get 8995.6 for taking M times C times delta T. When I take 11 joules, which is the coffee cup, how much heat it absorbs, times 21.5, which is my temperature change, I'm going to get 236.5. I add the two numbers together. So the total heat absorbed by the coffee cup and the water is 32.1 joules. That is the heat gained by the water. The heat lost by the reaction, I just add a negative sign. So now if I go back up here, my Q comes out to be negative 9232 joules. First thing is I have to convert it, or second thing is I have to convert it to kilojoules. So step 2, I just divide by 1,000. I ended up with negative 9.232 kilojoules. So I just did step number 2. Step number 3, I have to change it to kilojoules per mole, because the heat of reaction is always expressed in kilojoules per mole. I have my kilojoules on the top, which is negative 9.23 kilojoules. I just have to divide by moles. If you remember, all the molarities were 2O. Molarity times liters will always get us moles. Well, for both of the reactants, because you just base it on one reactant, each reactant will use 50 milliliters or 0.050 liters. So if I take 0.05 times 2, I end up with 0.10 moles. So that's how many moles I used. I used 1/10 of a mole every time we did a reaction. It's the same for all of them because every one of the ones we did was 2 molar, and every one of the ones we did involved each reactant was 50 milliliters on purpose. So I have 0.1 moles. So the last thing I do is I divide by 0.1 moles, and I end up with negative 92.3 kilojoules. Now this is way off. I'm just estimating it. You're not going to have a number that high, but that would be for one of my reactions. The whole point of this is, if I was doing the calculation, let's say, again, this is made up, but if I was doing the calculation and I just did that for my data from reaction 1, I would say my delta H for reaction 1 is negative 92.3 kilojoules. Well, then I'm going to do the same process for the next 2. I'm going to go through the exact same steps. Calculate Q using this exact same equation you see here. Grams of solution, specific heat of solution times delta T. Multiply all that, add in the calorimeter, the C for the calorimeter, which is just the heat capacity, and delta T. I get my value. I come up here, I divide by 1,000, so I convert to kilojoules. I'm going to divide by 0.1 for each of them, and I end up writing, and this is what I want you to bring to class. Where am I here? I would write in, I'm going to make one up, I don't know. Well, let's say this is negative 3.5 kilojoules, and then you'll find another one. You'll find this one. According to what Hess said, if you take 1 and 2, because you can rearrange, this is my target, you can rearrange equation 1 and equation 2 so they'll cancel and equal equation 3. Since you found the delta H experimentally for equation 3, when you take these two and add them together, it should be equal to whatever your experimental value was. That's the point of Hess's law. So tonight for homework, I want you to do the calculations for each of them. Find the delta H. You would write this out. I want you to have on your paper. You're going to do this all on a clean sheet of paper, or actually do it in your lab notebook paper would even be better. You're going to write each of these out. You're going to show each of the calculations separately. Make sure you label on every calculation. You label which reaction you're doing. Write the reaction. Do the calculations. And the last part you're going to do is add these two together and see if it equals the target equation. So you're looking to see if it equals the target equation. There's just another example I used. And we will do percent error when you bring it in class on Monday. So when you walk into class on Monday, you should have nice and neat, clear problem solving for each of the heat equation calculations. So calculate delta H for all 3 of the reactions. Then you should write out Hess's law like this, cancel it, like orient this so you equal this last reaction and prove, add the 2 together and see how close it is to the actual value. Actually, you can do percent error because your actual will be reaction 3, which you calculated. Your experimental would be when you add 1 and 2 together after you get them to cancel, and then times 100. That's how you calculate the percent error. Hope you guys have a good weekend. The other thing I would like you to do, if you get a chance, it will help review for next week, is watch the acid-based video. Acid-based video number 2. You were already supposed to watch acid-based video number 1. Have a great weekend. I will see you on Monday.